Hello and welcome back. In this lecture we are going to be starting more complicated problems which are going to use another number sequence for them to be derived. This is basically a sequence within a sequence. Fortunately, if you know how to represent the data, you can very easily solve the problem. So let's get straight into this. Here we are. The sequence is 4, 12, 24, 40, 60, 84. Now notice that the choice of small n, that is, you have to start counting from the left side, is not arbitrary. You can't assign n is equal to 1 to 84. You have to assign it to the number 4, which comes first. Now notice that all of the numbers in the sequence are multiples of 4. So let's write them by multiplying a number by 4. Here we are, every time a different number appears, 1, 3, 6, 10, 15, 21, all of them multiplied by 4. Let's separate these numbers and write a sequence within a sequence. Hold on, this looks awfully familiar. We just did this sequence. However, the old sequence was slightly different. It had 0 at the start. This one has 1 at the start. Fortunately, there is a way out of this problem. Remember, the expression for this sequence was n into n minus 1 over 2. So let's open this. And instead of n, let's write n plus 1. Let's open the expression in the brackets. N squared plus n divided by 2. This comes out to be n multiplied by n plus 1 over 2. Now let's put the values of n into this expression and see if we get a link between the expression that we found in the previous lecture and the one that we face right now. And we see that this is exactly the expression that we are needing. So, the two sequences are basically shifted versions of each other. This sequence here, this one, it has been shifted to the right. Now, if we want to find the expression for the first sequence, this one, all we have to do is that place n plus 1 instead of n in this expression, and this sequence is going to shift to the left. So, we have found an expression for the sequence within the sequence, that is n into n plus 1 over 2. Now let me clear the space. Now notice that every time this sequence is multiplied by 4. So, to get the original sequence, what we have to do is that we multiply this sequence within a sequence by 4. And so, we get an expression 2n into n plus 1. Now let's check our expression. We put n is equal to 4 in this, and the answer comes out to be 40, that's correct. Let's check with another one. We put n is equal to 2, this gives us 12. So, we have a confirmation that this sequence expression is correct. Now let's try a harder sequence. With this sequence, 5, 13, 25, 41, 61, 85. Now this looks a bit odd. Let's see how the two terms differ from each other. Interesting. All of the terms differ by different numbers. However, the numbers themselves differ by just 4. But that doesn't lead us to anything. So what does this lead to? That the numbers 8, 12, 16, 20, 24 can be represented as 4n. These are the numbers that are to be added to the previous value of the sequence to get the next value. Do you see the pattern? 4n, for 6 is 24, for 5 is 20, for 4 is 16. But this again brings us to the problem that we encountered previously, that we have to include the previous sequence. Whereas all calculations for the sequences are for the current number. For example, if we have n is equal to 2, we cannot take the help of n is equal to 1. However, this problem can be circumvented if we can figure out an expression for the previous part of the sequence in terms of the sequence number that is currently present. Let me show you. All of the numbers can be represented like this as well. However, notice that in the first sequence, this 1 here, where does this come from? Because we know that 5 and 13 and 25 are the values of the previous value of the sequence. Remember that all of the values of the sequence differ by certain numbers which themselves differ by 4. So we can say that if there was a sequence number before 5, the difference between that number and 5 would have been 4, and that number would have been 1. But that's not really necessary, and we can skip this term altogether. Here we are. So we are only considering n2, n3 and n4. If you can find a pattern for these, we can find a pattern for the entire sequence. We don't have to consider n is equal to 1. Now, 4 by 2, 4 by 3 and 4 by 4, it's very simple. This is 4n. Now, how do we find the relationship between n here and these numbers 5, 13 and 25 that are sequence values for a previous indice? This is obviously a case of a sequence within a sequence. Let me write this subsequence. Yes, this v indicates the value and n indicates the original indice. We have to just find the expression that links between 5, 13 and 25. We know the previous part of it, 4 by 2, 4 by 3 and 4 by 4, which is to be added to this. Notice that 5 can be written in terms of its indice 2 when we multiply the indice here 2 and add it to 1. Similarly, 13 can be represented in terms of its indice 3 if we multiply the indice by 4, add 1 to it. 25 can be similarly represented. So we have found another connection. Now what about this 2, 4 and 6? This is a further sequence within a sequence within a sequence. So now you understand what I was talking about, that these problems, when they get complicated, you need to be able to identify very quickly the mini sequences inside the main sequence. So let me write this mini sequence on the center of your screen. Here we have taken these values 2, 4 and 6 that you can see underlined to the left, bottom left of your screen, and place them with the original indices 2, 3 and 4. Now we have to find a third pattern here that links n with v. However, notice that these numbers look oddly related. For example, we can write 2 here as 2 multiplied by 2 minus 1, 4 as 2 multiplied by 3 minus 1, and 6 as 2 multiplied by 4 minus 1. Yes? So, this is going to give us a value of v in terms of n without having to dive further into another sequence. Simply 2 multiplied by n minus 1. Now we go back to the second sequence. That the numbers shown by the arrows represent n, and the numbers represented by the underline depict 2 multiplied by n minus 1, the sequence that we've just found. So we just have to multiply n with 2 multiplied by n minus 1 and add them to 1. See the two parts of the sequence. But our work is not complete yet, because we have to bring this sequence up to the original one. Remember that we were looking at the pattern for 5, 13 and 25, which themselves were part of a pattern that represented the original sequence. This part here was 4n, and the underlined part is the one at the bottom left of your screen. So we simply add them together. Here we are to the center right of your screen. Now we have to open this expression and simplify it. An expression 2n squared plus 2n plus 1. Now we have to check them. Put n is equal to 3 and we find the value of the expression as 25, which is correct. Put another number, n is equal to 6, and this gives us 85. So this is our answer, this expression here. 2 squared plus 2n plus 1. There are 3 sequences in total, 2 beneath the main one, and you find the last one and then you work your way up and find the main sequence. So this is the first heuristic that I have taught you, that you have to find the value of the sequence using the indice that represents it. You must not refer to the previous value of the sequence unless you can also define that with the current indices that we have done. So that's it for this lecture. We are going to be exploring some past paper questions from O levels next so that you understand exactly how these questions are to be attempted. Now, if there are any questions, please ask me in the comment section. I'll be very happy to answer them. Thank you for watching. The next video is present in the description of this one. Click on that link and see you in the next lecture.